Good morning. This is class 4 of our chapter Nuclear Reactions. Here we learn about reaction cross sections. First, the definition for cross section. It is a measure of relative probability for the reaction to occur. Suppose that a particle B is emitted in a direction theta phi with respect to beam direction, and let a detector is placed, and that detector defines a small angle d omega at the target nucleus, and it is shown in the figure given below. Now let the current of incident particles be Ia particles per unit time, and let the target show to the beam n target nuclei per unit area. Now if the outgoing particles appear at a rate Rb, then reaction cross section is given by this formula. So reaction cross section is denoted by sigma. It is given by Rb by Ian. What is Ia? It is the current of incident particles per unit time. Rb is the rate of outgoing particles, and capital letter N is the uh, uh, number of target nuclei per unit area exposed to the incident beam. This is equation 1. Now in this way, sigma can have a dimension of area per nucleus, but it can be very large, or it can be very small than the geometrical area of the disk of the target nucleus seen by the incoming beam. Now sigma is a quantity which have dimensions of area, but it is proportional to the reaction probability. Now as already said, our detector occupies only a very small solid angle d omega. Therefore, it is not possible for the detector to observe all the outgoing particles. Hence, it can observe only a small fraction of the outgoing particles, say d or b. Okay, as a result, only a small fraction of the cross section, say d sigma, will be calculated, or it will be deduced. Moreover, another thing is that the outgoing particles, that is the particles emitted, may not be emitted uniformly. That is, they will spread in all directions. That is, they will have an angular distribution which will depend on theta and on phi. So, let this angular distribution function be represented as r of theta phi, then drb will be equal to r theta phi d omega by 4 pi. Now here 4 pi is introduced to make d omega by 4 pi a pure fraction. So the cross section will become d sigma by d omega will be equal to r theta phi divided by 4 pi ia n. So now this quantity d sigma by d omega is called differential cross section, and it gives us information on the angular distribution of the reaction products. In some literature or in some books, you can see it as represented as sigma of theta phi, or simply sigma theta, or simply cross section. Now the unit of differential cross section is barns per steradian. Okay, so this is differential cross section. So these three slides are very important when you are writing about cross section. Now let us find the reaction cross section sigma by integrating d sigma by d omega over all angles, taking d sigma d omega equal to sin theta d theta d phi. So integrating sigma equal to integral of d sigma by d omega, it will be equal to integral of 0 to pi sin theta d theta, again integral to 0 to 2 pi d phi d sigma by d omega. Now here d sigma by d omega is a constant. Now the insertion of the constant 4 pi into equation 2 for r of theta phi will now reduce to the constant rb, and equation 2 will agree with equation 1. So in place of this one, we are writing, instead of r theta phi in equation 2, we are writing rb, and 4 pi we are neglecting. So d sigma by d omega equation 2 will have the same form as that of equation 1. In nuclear physics applications, actually we are not concerned with the probability to find particle be emitted at a certain angle. We also want to find it with how much energy corresponding to a particular energy of the residual nucleus y. That is, we are not concerned about the particle emitted. Instead, we are concerned about the particular energy of the residual nucleus. Let that be represented by the letter y. So, we will now have to modify the definition of cross section just to give the probability to observe the emitted particle B in the angular range d omega and in the energy range dE. This is called doubly differential cross section. That is, we are including both angular range d omega and the energy range dE. So, the differential cross section will now become doubly differential cross section represented as d square sigma by dEb d omega. Now, if you do not observe the particle that is, if you do not observe the direction of particle B, then we measure another differential cross section, and it is given by d sigma by dE. Here E will now represent excitation energy of Y. Y is actually the residual nucleus. Okay. Now there is another cross section, that is total cross section, that is sigma T. Here, for a specific incident particle, say A, we add the reaction cross section sigma for all possible different outgoing particles B. No, we are not bothered about their direction or energy. Okay, such a determination will tell us the probability for an incident particle to have any reaction at all with the target and thus be removed from the beam of incident particle. So this can be calculated directly by measuring the intensity loss of a collimated beam after passing it through a certain thickness of target material. So that is about total cross section. When we discuss a specific reaction, then the exact meaning of the term cross section will depend on exactly what we measure. Okay, for example, if we wish to produce a radioactive isotope as a residual nucleus Y, what we have is, we are not interested in the direction of emission of particle B, or we are not interested in the excited state of the residual nucleus Y. Okay, for they, why? Because we are not interested means because they will quickly decay by gamma emission to the ground state of Y. So there is no need of understanding about the residual nucleus Y. So, okay, so the literature often does not distinguish carefully among these definitions, and often they are called merely cross sections. That is why certain literature total cross section, they just write like cross section. Okay, it is almost always obvious in context which cross section is meant, and therefore not strictly necessary to distinguish carefully among them. Okay, so here in this class we are discussing about various cross sections, its definition and the expressions. One is total cross section. This is about total cross section definition and its significance. Then we have studied about doubly differential cross section. Then we have studied about simply differential cross section, and then we have studied about simple cross section. Okay, then this table also you have to refer. This actually tells us about the various cross sections. One is total, reaction, differential angular, differential energy, doubly differential, and its symbols are given, the technique used are given, and the possible applications. So this table is important. This you have to study along with the points that we have discussed here. Okay, thank you.